All right, good morning. How's everyone doing?
Doing well, Nick. How are you doing?
Doing well too, thank you. All right, any questions?
I have a question.
Okay.
For the homework assignment for creating Git repositories,
Mm-hmm.
would it be okay? Uh, would it be okay if instead of doing like homework 001, do homework 101 or 201, so that they do not clash with the previous courses Git repositories?
Yeah, that would have been a good idea, but it's kind of too late at this point. It's got to be 101. You could probably rename the old 101 repository to something else to move it out of the way.
Luckily, it's not a 101 repository, but for 002 and past that, all those namespaces are filled already. Do you want me to just rename those then?
So going forward, I'll use more creative names for the repositories.
Alright.
Or I'll try to. What did I ask for on PA1? Let me see.
Homework 001.
Now for the first programming assignment. Let me see. Yeah, so the first programming assignment is going to be a repo named linked list 1, so that shouldn't conflict. So I'll try to stick to more descriptive repository names for future assignments. But for 001, just move the old one out of the way if it conflicts.
Alright. Thank you.
Yeah. Alright, cool. Other questions? Everyone good on the homework? Good on the ODP? Good on the quiz? All right, well, let's go on and let's talk about data structures. Oh, before we do that, let me just mention something that I mentioned in the A section yesterday. For service learning project proposals, if you go to engrcs.com and come down here under ECS Club and scroll down to the bottom, you'll see sample of past student projects. You can find a YouTube channel of videos that students have offered to share of SLPs that they did in the past. So this can give you kind of an idea of some of the projects people have done, right? Just sort of get an idea of scope and creativity level and stuff like that, for what it's worth. Let's see. So somebody asked, oh, how do we send email in Linux? So let's do that. So if you want to send me an email, just say mail Nick. And it'll ask you for a subject, and for you this would be git : space and whatever your repository name is. And then if you had other things you wanted to tell me, don't do it for this assignment, but if this was something else, you could type your message here. When you're done typing in your message, just hit a period and an enter key, or do a Control D. And as long as that's the first thing in the line, that will end your mail message. And if you didn't type anything in except a subject, you get this message saying null message body. Hope that's okay. That's perfectly fine. So that's sending mail. Let me make these sticky. All right. Quiz was difficult. Yes, indeed. Made a script to add and commit work and Git, but someone mentioned hooks online. Are these better than using custom script for any reason? So if you actually use an API, right, you could, I don't know, control it from a C program or tie it to a web page or something like that. I would absolutely just go with a script. I mean, that's what we did in 224. That's why we learned Bash. If you want to dig into deeper stuff, right, you can dig into that, and it might give you more control, but script should work perfectly fine. All right, let's see. Student project declarations due. Yes, January 13th. Good. Thank you for sharing that. Link for Discord. Somebody posted it. Presumably that's the right link, but it should be on Canvas also. Cool. Good stuff. All right. Other questions? For homework 1, should email subject be git :username instead of repo name? Yeah, it's your git user ID, not the repository name. For PA1, does the folder have to be linked list? The folder can be whatever you like. All I'm going to do is go to GitLab and pull down a repository named linked list 1. So whatever you call it on your own system, that's totally up to you. And make sure it's uppercase L's on linked list. And we'll talk about that programming assignment 1 in detail at the end of the week. I want to get through a bit more on structures and data types before then, but Thursday or Friday probably we'll go through that in detail. All right, and somebody just mentioned there's a Discord server run by students for STEM classes in general, not just CSE. So check that out. There's a link to it on chat. All right, let's talk about data. That's the first part of data structures, right? So, so we have different data types available in C, right? We have integers, we have characters, we have floats, we have doubles. What are some other data types we have? What other types of data we deal with in C? Longs. Long. Structs. Constants. Unsigned. Pointers, someone said it. Address. There's a file, there's a Boolean. So there's a whole bunch of types of data that we interact with, right? So we know what integers are, right? They're 16 or 32 bits. They're positional weighted representations of integers, positive or negative usually, using 2's complement. Characters are just bytes, right? Okay, there's the part that was missing, arrays. Characters are just bytes. They're the simplest to work with, right? Floats are 32-bit numbers, doubles are 64-bit numbers. They're coded using IEEE 754. And, you know, part of that 64 or 32-bit is a sign bit, part is an exponent, part is a mantissa. You put them together in the right way and you get a real number. So these are built-in types in C. A long is a particular type of integer, has a different length from perhaps a default int. A long is another type of integer, and unsigned is an integer that treats negative numbers differently. It treats them as just bigger positive numbers. But these are ways of interpreting what an int is. Arrays are collections of data, right? Pointers are something that refers to a memory location, and pointers and arrays are kind of the same thing. And somebody else said, aren't pointers just integers? Pointers are some kind of integer. They might be a long integer or a long integer, but they're somehow related to integers. An address is some type of integer also. File is not a built-in type in C. It's a composite type that's actually going to be an example of a structure. So let's just start with these four basic types: integers, characters, floats, doubles. And let's think about memory on a computer. So memory organization. So we're going to draw a lot of memory maps in this class. So a memory map is, you know, a rectangle with the word memory on the top, and boxes for storing stuff, and addresses. And, you know, we might write down the contents of these boxes, and some of them might be unknown, or they might be characters or ints or who knows what, right? So we'll draw a lot of pictures like this. What does the memory actually look like in hardware? And the PIC processor that we use in 270 is kind of an unusual case. Its memory is built in, and we don't actually use the word memory. We use the word file register to describe memory locations. But on something like, you know, an x86 machine, a laptop, a cell phone, what does the memory actually look like? I mean, it's not a green rectangle with lines running horizontally. But how close have you gotten to actually looking at the actual memory of a computer? Because remember, we have our basic setup. We have a CPU, and the CPU basically sends an address to the memory, and then it exchanges data with the memory. And the basic setup is instructions are stored in here along with data, and so the address of the first instruction of your program is sent to the memory, and the CPU says, tell me what's at that location, and the data for that instruction goes into the CPU, and it looks at it and says, oh, that's a clear instruction, right? I'm supposed to clear something, so what should I clear? Well, it'll send another address and find the operand and read that back, and so on and so forth. So yeah, you've written x86, so you're very close to the middle. And yeah, physical hardware or in the software level. So I did not plan this, right? This is purely coincidence, but I've actually been working on a sort of retro setup of a small microprocessor system. So So this is a large version of something that's going on inside your cell phone. So it's buried under wires, but there's a big chip over here. It's 40 pins, right? It fits in a breadboard nicely, so it's the standard spacing from our 250 class chips. That's a 40-pin chip. That's a microprocessor. It's an old processor called a Z80. It's an 8-bit microprocessor. Over here is another chip. This is a 28-pin chip. And this is memory. This is a static RAM, 32K by 8 bits. And all of these wires that you see are basically the communication lines where the CPU sends an address to the memory, and it also shares data with the memory. And the Z80 is an 8-bit processor, so it's an 8-bit data bus. So 8 bits gets transferred at a time. And no, I'm not making a Spectrum clone. I'm actually making a credit card size version of the old MSI 8080 board. Just because I've discovered the joy of doing surface mount work, and I want to make more surface mount boards. So that's my current project. All right, so we have these different types of data. We have integers, we have longs, we have floats, and so on and so forth, and they all get stored in this memory. The first thing to note is that this memory is basically 8 bits wide. Now it's physically wider than that, right? On most machines, your DRAM is not organized in 8-bit chunks. It's much wider. 64 or 128 bits across. But architecturally, when we think about a memory address, we're referring to something in these 8-bit chunks of memory. And this is important to know because a lot of times what we have in our memory are things like ints, which is 32 bits, or 4 bytes. And if we have some integer called x, and x is, stored at, say, this location in memory, well, in practice, at that particular location, we only find 8 bits. So if x is an integer that's 32 bits, where are those other 24 bits stored? And not surprisingly, they're stored in consecutive locations. So these 4 bytes would correspond to the integer x. Well, when we look at the address of x, it refers to a single byte in memory. All right, so let's write some code. So there's some code. I've got x, it's an integer, and I'm setting it to a hexadecimal value, 1, 2, 3, 4, 5, 6, 7, 8. Just for no particular reason. And I'm going to compile it with debugging symbols. And I'm going to debug it with GDB. And I'm going to start, and I'm going to do this one assignment statement. All right. Yeah, so someone asked memory indexes would be like 0, 4, 8, and so on. The way that we think of them, yes, but architecturally, it's still consecutive bytes. So let's put those two concepts together. So here's our variable x, right? How can I figure out where x is stored in memory? I can look at its value by saying px. That'll show me the value. I can print it in hex and see, 1, 2, 3, 4, 5, 6, 7, 8. But how would I figure out where in memory this variable is stored? So yeah, we can use ampersand x. So ampersand x means the address of variable x. So if I print ampersand x, I get this crazy number back. 7FFF, FFFF, and then EAEC. So at this location in memory, supposedly that's where my variable x is stored. So if I examine that location in memory, I find 1, 2, 3, 4, 5, 6, 7, 8. But what I'm telling you is that there's only a single byte stored here. So in GDB, I can say examine the byte stored at that location, and what do you think I'm going to see? I'm going to see a 78. And it's not an ASCII code because x is an integer. So it's storing the binary representation of that integer. It's 32 bits, weighted positional notation. So at this location, I see hex 78. All right, now if I just hit enter, it should show me the next location in memory. So this is EAED, and that's got a 56 in it. And if I go down to EAEE, that's got a 34. And if I go to the next location, EAEF, that's a 12. And just for fun, we can go on to the next location, and that's an F0. So we're building a memory map. And we know that X is stored here, because that's what the address of X returns, is this EAEC. But we need to know that X is an integer, and that on this system, integers are 4 bytes. Well, how do we know that integers are 4 bytes? Print size of int tells me 4. So X occupies these 4 locations in memory. And since our memory is only 1 byte wide, 8 bits, we have to break our number X into 4 pieces, 1 byte each, and store those in sequential locations. And the peculiar thing to note here is that at the address of X, we find the least significant byte, followed by the next most significant, the next most significant, and ending with the most significant byte. So we've taken an int, which is 4 bytes, and we've figured out using the debugger how that int is stored in this 1 byte wide memory. Stored least significant byte down to most. Now, is that the only way we could have done it? No, we could have stored the most significant byte first, and then the lesser, and the least significant byte down here. Would that break anything? Not at all, as long as we were absolutely consistent about it. It's completely arbitrary which way you store these, but you need to know, right? So yeah, this is a notion of encoding, and this is what's called big endian versus little endian encoding. And some machines do it like this, some machines flip it around. This can be a problem if you're taking data from one machine and trying to use it on a different machine. If your integers are stored flipped around, your numbers look different. This can be a problem with networks, because networking, you're always swapping information from one computer to another. So there's some standardization for networking as to how integers are stored. There's what's called a network order, right? But the host order can be totally dependent on your particular CPU. All right, so that's the first piece of our story. So let's talk about strings. So when we make a string, we're really dealing with an array, right? So a string is just an array of characters. But this notion of an array, remember, is actually just a pointer to a single character. All right, so let's work with this. So let's make an array of 120 characters, and let's just run this code in GDB. All right, so X is stored somewhere different now. So let's make our memory map. So the address of X is 7FFF, FFFF, EA6C. All right, we also have a string. Well, if I print out my string, it will show me the value of my string because GDB knows that S is a pointer to a character array, pointer to a character, right? And I set it up to have 120 entries, so it will show me the 120 characters stored in S. Well, there's 29 nulls, there's a 377 octal, there's 18 nulls, there's a T time with a null and some other stuff and so on, right? But let's see how S is stored. So if I print the address of S, it will tell me EA70. So now let's make a new map. So EA70, that's where S is stored. EABC, that's where X is stored. And remember, X occupies 4 locations, starting with least significant byte, going down to most significant byte. S takes 120 bytes of storage because each character takes a byte. So S begins at EA70, but it should occupy the next 120 locations. And so I can be more specific here. Let's print the address of S bracket 0. That's EA70. Right, so this location right here, this is S bracket 0. I can print the address of S bracket 1, and that's EA71. So S bracket 1 is stored in the next location. So you can use GDB to play all these kinds of games to explore your memory layout. And this is something we want to get good at. Okay, because what we're going to be doing is we're going to be manipulating memory by ourselves through C code at this very low level. And when we're debugging, we're going to need to know how we think memory should be laid out. And we're going to need to go into GDB and do these kinds of investigations to see how memory actually is laid out. And then if there's a disconnect between those, which is usually, what our bugs present as, then we need to go back through our code and figure out how to find out where that disconnect happened. All right, so what's the index of the last element in the array S? $1,000,000 of SpongeBob money if you give me the answer first. What's the address of the index of the last element in S? 119, good. I'll send you your $1,000,000 of SpongeBob money. So let's print the address of S bracket 119. So that's EAE7. That can't be right. You're rich. I made a typo. All right, so our array S goes from EA70 to EAE7. So there's the end of our S array. And X, I typoed when I copied here. It's actually EA6C, 6D, 6E, 6F, and then EA70. So X is actually stored before S. So let me just do a quick remap of this. So this up here is X, this down here is S. This is the least significant byte, this is the most significant byte. This is S bracket 0, this is S bracket 1, and this is S bracket 119. So there's our memory map for this particular pair of variables that we've declared. All right. So GDB is useful for this, right? If I print the address of S bracket 1000, it shows me, you know, an address, FFEE58. Well, S doesn't have 1,000 elements in it. I declared it to hold 120 characters. But it doesn't care about this. It will just go ahead and calculate, you know, if there were a 1,000th element in this array, what address would it be stored at? This address right here. And yeah, this is interesting. Because, so we declared X followed by the character array. X got stored first in memory. That's not guaranteed to be the case. It is up to the compiler. So this is another reason why we want to be able to go into GDB and look at things. The other thing is things are not always stored consecutively, one right after the other. Sometimes there's padding. So for example, integers always start at an address divisible by 4, because that makes your code a lot more efficient. So if I had a character declared first and that character was stored right here, the next 3 bytes in memory might be, if I had a character stored right here, the next 3 bytes might just be unused, and my integer might start down here at location 70. So integers, a lot of variables want to be aligned on certain multiples of typically 4 or 8 or possibly 16. And that's a nod to the realities of how memory is organized and how memory management systems work and how fetches are done from a memory subsystem. And if you don't align these things, your code gets really inefficient. So that's a computer architecture notion. All right, so I can print out, you know, element 1000. I can print out element -1. And what's the address of S bracket negative 1? It's EA6F. Well, EA6F is actually the most significant byte of our variable x. So in my C code, if I were to set x bracket negative 1 to some value, I would end up changing the value of x. Now, whether the compiler will let me get away with that remains to be seen. But there you go. So what do I have? I have a integer x, which I've given a value to. And then I changed an element in my array s, and I printed out the value of x again, and x changed value. Well, there's nothing mysterious going on there. S bracket negative 1 is the address of this most significant byte of x. Am I setting that equal to some number like 123 in this case? I changed the value of my variable x. So this is all just memory. It's just bits stored in memory. And we normally interact with those bits in a very controlled way, right, through a language like C and a program that's put together. But really, you're just manipulating bits. When you get down to the level of the CPU executing instructions, it usually doesn't have any idea what it's doing. And if you do something bizarre like S bracket negative 1, what does the compiler do? Well, it generates assembly language code which says take the address at which the array S begins, take negative 1, multiply by how many bytes we need for an integer, add that to the address, use that as the address where we want to store 123, and store 8 bits using that. So, good question here in chat. How does a program keep track of what data type a variable is? Is there a memory location that maps a variable that identifies its type? Is this done by an OS or something else? The terrifying answer is the running program has no idea about data types. Absolutely no idea. It's up to the compiler and the programmer to some degree when they're writing their code and when the code's being compiled. It's up to that aspect of the process to do whatever needs to be done to make sure that appropriate data types are used. So for example, if S was declared to be an array of integers, and I said S bracket negative 1, this would be referring to a location 4 bytes before the address of S. Since the compiler knows that S is an array of characters, it calculates this as the address of a location 1 byte before S. But it's totally up to the compiler and the linker and initially the programmer to put those things in place. Once this is compiled into executable code, there's no notion of data types anymore. And that's pretty intrinsic to compiled languages, right? We kind of throw away that information. Those are organizational constructs that we use as programmers to, describe what we want done. But when we get down to the CPU, it's just bits. Bits in byte-oriented memory locations. Which can be terrifying if you think about it too much. But it lets you do cool stuff like this. Can you mess with other systems using the negative 1? Sure. You can do all kinds of stuff with this. Now, if I go to too much of a negative index or too much of a positive index, I'll step on areas that I don't have access to. And I'll usually get some kind of error from the memory management system, and it will come back as a seg fault. But if you're judicious in your use of this, you can do all kinds of things, including security issues. So this is where buffer overrun attacks basically derive from. A buffer overflow attack basically, takes advantage of the fact that your program may only have a certain amount of memory allocated to store, your username in, for example. And if you exceed that buffer by typing in a longer username, you can potentially start changing the values of other variables in the memory of the program. Oh, very cool. So yeah, someone just commented in chat they made an x86 tic-tac-toe game and stored the entire game board in 15 bits and used the remaining bit to indicate who was playing, whose turn it was. So 2 bytes to store an entire tic-tac-toe state. And yeah, at the assembly language level, we often go down to the bit level. Right? Now C, we pretty much don't go below the byte level, and even though C understands bit fields, they're mostly treated as bytes. But assembly language, we can go down to individual bits, and within one 8-bit byte, or one, say, 32-bit integer, we could store multiple pieces of information. A single int can hold 32 Boolean flags. And if memory is precious, sometimes we want to take advantage of that. All right, so that's how arrays get laid out. There's a fundamental issue here, though, which is if everything is just locations in memory and bit strings, how do we know in our code that this array S has only 120 characters? What's to stop us from trying to access this next location? Now, our code's probably not going to look for S bracket -1. That's just something we do to be goofy. But how do we know that there's only 120 possible characters in our string S? Well, with strings in C, we have a little trick. So strings were originally intended to store ASCII characters, and ASCII character codes for all the characters that we would typically type or look at start at 32 and go on up. And there's uses for the codes below that, like an ASCII code of 7 used to ring the bell on the side of your terminal, for example. An ASCII code of 10 means go down to a new line. But there's the special ASCII code 0, which we don't normally encounter. And so when people write a string in C, there's this expectation that 0 is not going to be part of your string. So we use this as a special character to say this is the end of the string. So this is the null terminator. And when we have an array of characters, at some point we store this null, which we can write in single quotes as a \0. And the understanding is everything up to that point is the string. The 0 means the string ended. So yeah, that's the reason for the null terminator. So that's a nice trick for strings, but it doesn't work in general. If we have an array of integers, we can't use 0 to mark the end of the array because, maybe 0 is a possible legal value in our array. Maybe these are, arrays of temperature readings, and 0 degrees is a valid temperature reading. So how can we indicate the end of an array of integers? We can't. And this is a fundamental notion of C. Arrays don't have a discoverable length. An array has a certain length. We've allocated a certain amount of memory. We've stored a certain amount of information in there. But if I just hand you this array, there's nothing you can do to figure out how much information is stored in that array. Because what is an array? It's just a memory address. It's the address of the first element in the array. So when you hand someone an array, all you're doing is handing them a location in memory and saying, yep, there's an array stored there. Well, how many things are in the array? Who knows? It's not part of the language. All right, let's see. Chat questions. Ugh, the bell. Oh, what's wrong with the bell? Bells are cool. How is memory managed for arrays of the same name between different programs? Pretty easily, actually, because when you get down to running the machine code, the variable names are completely gone. Everything's been changed into addresses. Now, when you're compiling, if you have two functions with the same names, the compiler keeps track of them as separate. Right? I'm in function 1 and I have an array called S. I'm in function 2, I have an array called S. It thinks of this as, S in function 1, thinks of that as S in function 2. They're completely managed separately. Now, if you have a global variable named S, right, then anywhere in my code that doesn't declare an S locally will refer to that same S. But if I have a different program with the same variable, that's compiled separately, and those compiled pieces have information saying, this needs to go somewhere in memory. This other piece will say this needs to go somewhere in memory. The linker will keep them separate. Understanding how code gets compiled is fairly straightforward until you start digging down into the memory. And when you start trying to link pieces of code together, that's when you start really understanding like how these things turn into an executable program and how the operating system runs that program. It's a really good exercise for exploring those aspects of programming. For some reason they decided that strings in MS-DOS would be terminated with a $sign, so you have to use a different method to point. Yeah, MS-DOS is good that way, and they use Control-Z for end of file, or at least they used to. So if you have an ASCII character 26 in a binary file, it was hard to read it because it would mark end of file, so that was annoying. Hey, welcome, glad you're here. How does a compiled program detect an out-of-bounds error then? So if your array goes out of bounds, normally there's nothing to tell you that happened. You can set up protected areas of memory around arrays, and you would get an error from the memory management subsystem if you tried to access that. Or you can arrange to have extra code generated so that when you access an element in an array, first it checks to see if that index is legal or not. And so you compile in extra information that lets it do bounds checking. And these things, take a performance hit in exchange for adding these capabilities. Is that the reason we don't use scanf versus fscanf because of overflow problems? So it's the reason we don't use gets. It's the reason we use fgets instead of gets is because of that overflow potential. The reason I don't want people using scanf though is slightly different. That has to do with being able to parse input multiple times. Size of is just a while loop until \0. No, size of is a compile command. It doesn't actually turn into executable code. The compiler replaces it with the size of whatever data type you specify. String length is a loop until \0, right? Yeah, you probably meant string length. All right, small unrelated question. We are out of time here, so you're welcome to take off if you like. We'll talk about structs tomorrow, but let me go ahead and address this one question. Otherwise, have a good afternoon. Let's see, I have a small unrelated question. I'm trying to work on the homework, but I have leftover directories from 224. I can't delete these directories outright because of the get information in them. Do you have knowledge of something that can delete a directory even if it's important? So you can just rename those directories. You can actually delete them, but you can call your directory whatever you want, right? The repository should be called homework 001, and if the repository already exists on GitLab, go into GitLab and either delete it or rename it. And the future repositories, I will go ahead and use distinct names that are different from what we used in 224. I moved rm-r, but the Git files are protected. You can do rm-rf, but that's a little dangerous. Yeah, it would be better to just rename the whole directory. If you have a directory homework 001, just rename it using mv, and then it's out of the way. Because rmrf will eventually get you into trouble. At some point, you'll wipe out your whole directory tree. So I would avoid that. Let's see. Quick question. When I got to the do push origin master, I got a failed error saying something else might be trying to push. I don't know about something else trying to push, but that is either your repository already exists on GitLab, or maybe a typo when you did git remote add origin. Failed to push some refs to GitLab Gershon linked list 1.git. And you did your git remote add origin already? I'm going to stop the screen recording here.